Okay, welcome back. So last time we began talking about sequences. Sequences, we defined what it meant to be a sequence in a metric space. And we talked a bit about how to think about sequences. How do you prove that a sequence converges, for instance, convergence to a particular point. And so what I want to talk about today I want to say a little bit more about sequences just to warm you up a little bit. And then we want to talk about subsequences. What are the relationship between sequences and subsequences in particular? And what does it mean to be a Cauchy sequence? And so that's the plan for today. So let's just start up with a little bit of warm-up. You recall from last time we had a definition for what it means for a sequence to converge. So we say Pn converges to P if a certain condition holds. Okay, and what is it saying? Well, what it's saying is if you have a bunch of points of a sequence, and we'll say that they converge if, to let's say some point P, if what's true? Well, if no matter what epsilon you give me, there is some point in the sequence beyond which all the points are within epsilon of P. That's basically what that definition says, right? For every epsilon bigger than 0, there is an n, an integer n, such that any point in the sequence beyond n will live within epsilon of P. Okay, that's what it means to converge. We write this in a couple of different ways. Pn converges. We write arrow P or limit of Pn as P. Okay. Okay, so and we explored that last time and saw many different consequences of this fact. But let's explore a little bit what happens in R or in C. So let's consider. So maybe let's just warm up. Suppose we have a sequence Pn. Let's say consider sequences Sn and Tn. And these are sequences, so I'll write them as a collection here. Suppose these are in C. Okay, if you like, just think of them in the real numbers if you wish. But anything I'm about to say will be true also in the complex numbers. And suppose that they're convergent sequences. So let's suppose that Sn converges to S and Tn converges to T. Okay. Then I claim the following things are true. So here's a few theorems. Let's just see if we can prove them. Here's a theorem. I claim that if Sn converges to S and Tn converges to T, that in fact, here's a basic theorem, I can say something about Sn plus Tn and what it converges to. Take a wild guess. S plus T. Good. Let's prove this. So how are we going to prove this fact? Now, I want to remind you that that definition up there, it basically begs us for every epsilon to find an n, right? So that's the goal, right? This is the whole name of the game here. The important idea of this theorem, so the important idea of this definition is always of that definition is always to find an n. So to converge to show convergence, you have to find an n. You must find an n. So to show convergence, you must find an n. That's your goal. Okay. For every epsilon. Okay, you're given epsilon, you must find an n for every epsilon. So let's see how that plays out in this proof. So we're going to prove that basic little theorem. How are we going to prove that? So let's see. What are we trying to do? We're trying to bound some distance, right? The distance between Pn and P. And so here we're trying to bound what distance? The distance between Pn and P, the proposed P, right? So we want to show that Sn plus Tn is close to S plus T, yes? Now, what do you know? What are you assuming, given the assumptions here? I heard some of you whisper. Go ahead and say it aloud. Excellent. Thank you, Keith. Sn is close to S, and Tn is close to T, right? You know that's small. You're trying to show that this difference is small, right? So let's, before we do the proof, let's just say what the idea is. So the idea here is we want to bound. We want to make certain something small, Sn plus Tn minus S plus T. You're trying to show that this is small, yes? In fact, you're trying to show that's less than epsilon for some given epsilon, right? You want to know at what point in the sequence is that thing small? Okay, so now what do you know is small? Sn minus S and Tn minus T, as Keith said, right? So can you see a way to bound this in terms of two things you know are small? Some of you are nodding yes. Show me how. It's less than or equal to, just split it up and use the triangle inequality. And the idea is to use this bound, right? Okay. And now this is going to be small eventually. So this will have to be small eventually. Okay? Now, of course, the two eventuallys might happen at different places, right? If you want this thing to be really small, it might not happen until n is bigger than 100. And if you want this to be really small, it might not happen until n is bigger than 1,000,000. So if you want this to be really small, you need n to be what? 1,000,000. Okay? Sort of see where we're going with this. I have not written down any part of the proof yet. This was just the idea. Okay, good. So let's start the proof. So we'll start with by fixing an epsilon. So given an epsilon bigger than 0, would you agree? Now we're just going to state what we know, which was what Keith observed, that Sn minus S is small eventually, using that definition. So given epsilon bigger than 0, to say that Sn converges to S means there exists a what? N. And I'm going to, in fact, because I see I'm going to need two different n's perhaps, I'll call one n1. There exists an n1, and in fact I know another one's coming up, so I'll just go ahead and say that here too. And an n2 such that, okay, help. Well, such that if n is bigger than n1, this is going to imply what? Sn minus S is less than whatever I want, right? Of course, connected with that given epsilon, but whatever I want here. In fact, it doesn't have to be connected. I could say Sn minus S is less than 10. There is a point in the sequence where that's true. Or less than 0.4, right? But what I see that I need because of this idea is I want to show this is less than epsilon. So it'd be nice if I could show that these things are small enough so that their sum is less than what? Epsilon. So what would you like to pick? Epsilon over 2. And I know there's also a point in the other sequence beyond which what? Tn minus T is what? Less than epsilon over 2 as well, right? Comma, period. Okay, and of course you'd write out implies if you were writing this out formally, as well as there exists. Okay, now we're in pretty good shape now, and so now your job to show convergence of the sequence Sn plus Tn is to find an n for that epsilon we started with. At what point in the sequence is this difference going to be less than epsilon? For the maximum. So we should tell the reader what that n is. Let big N be the maximum of n1 and n2. And now, of course, you should finish by justifying for the reader why your n works. So this is the claim. This n works. Why? For n bigger, so then, for little n bigger than big N, we have, and I'm just repeating this observation, Sn plus Tn minus S plus T is less than or equal to Sn minus S plus Tn minus T, which is less than, strictly, what? Epsilon over 2 plus epsilon over 2, which is epsilon. And the important parts here is you've shown this is strictly less than this, as desired. So the first few times you do this, of course, you just tell the reader your conclusion, which is that Sn plus Tn converges to S plus T. But once you start becoming more mature, it's probably okay to just stop here, because everybody's seen a proof like this before. Okay, but the first few weeks that you do these proofs, you should just remind yourself what you're doing and remind your reader. Okay. Okay, so we just did a very simple example of this because it just points out a very key technique here. One sequence converges, maybe not as fast as the other, but your job is to find a point in the sequence beyond which both these things are small enough to bound this. Happy? All right, any questions? Okay, now I'm going to let you help me with the next justification, which is similar enough. Tell me what you would do for the following theorem. Again, I'm going to assume for the next several theorems that we have these assumptions for Sn and Tn. Do you think it's true, or what do you think is true about this sequence? What's the limit as n goes to infinity of a multiple of S of Sn? So limit of Csn, where C is a scalar. It's CS. Okay. Yay for CS. Okay. Let's see. Actually, here's another thing that's true. The limit as n goes to infinity. What if you add a scalar to Sn? What do you think that converges to? The sum of C and S, right? Okay. Okay, we'll just do one of these. But tell me what the idea here is. Maybe let's just do this part. What idea do you think is going to help us show this? For this, as CSN converging to CS. What bound am I interested in? What am I interested in bounding? Good. Let's bound CSN minus CS, and that we hope is small eventually. Yes? What do we know is small eventually? Sn minus S, right? Okay, so Zach is thinking, how are we going to connect this value to the value of Sn minus S? Oh, can I do that? Is this equal to or less than or equal to something? How would you suggest we do this?
Well, it's equal to absolute value of C parenthesis S.
Okay. There's the operative idea, isn't it? Right? Again, this doesn't have to be this is not part of the proof, right? This is just something that, in fact, if you're writing up the proof, you wouldn't tell me what the idea is, right? You just go ahead with the proof. But this is sort of the scratch work you'd do, right? Okay, good. So help me. I should probably start off by telling the reader what the assumption is. So here we go, proof. Yep, given, or sometimes we just tell the reader we're going to start with an epsilon, fix epsilon bigger than 0. It's an alternative way of saying this, doing the same thing. Okay, then there exists, help, an n such that n bigger than big N implies okay, yeah. You know, sometimes when you start this proof, you're not exactly sure what needs to be here, but you can always go back and change what you to make this work, right? But if you've already seen the idea here and you want this less than epsilon, what do you think this should be less than? Epsilon over c. Okay. With me on that? So now, once you have that, then you're in good shape. What's the n that works to show that this is small? The same n. Yes, very good. The same, whenever this is small, whenever this is. So for this n, and I'm just underlining it to emphasize, we've done what we were asked. We found an n that works. N bigger than big N implies CSN minus CS is equal to this, which is less than, you can finish it out, but it's less than epsilon because of the epsilon over C. Okay? As desired. Have I done what I was asked to do? Yes, I found an n that works. Oh, I'm feeling guilty for not saying, reminding the reader what we've just done. So CSN converges to CS. There we go. Okay. All right, excellent. Not going to do this one out, but can you see what the operative idea is here? Yeah, in fact, you'd use the idea that C plus Sn minus C plus S is what? Equals Sn minus S in absolute value, right? You can do that one. Okay, let me write a few other things that are true. Here's one. Help me. What can I say about products? What can I say about products? Take a wild guess. Do you think it's S times T? Always? Yeah. As long as those conditions hold? Okay, sure. Okay. Okay, this one's a little more interesting. Tell me what you think the idea should be. First of all, what should I be trying to bound? SNT and minus ST. Help. This one's a little more fun. Steve and Maya have a suggestion? Anybody? Kim? Ian? Drew? Add and subtract. Yes. Okay. Good. Yeah. So this is kind of one of the you can't stop me from doing this. There's actually many ways you could handle this, but here's one way to handle it. It turns out that if I look at this product, which is a natural thing to try, of course you get an SN and a TN, and you get an S and a T, but all the signs are all wrong, and there's a few cross terms as well, right? But this, if I add STN minus T, and I add T times SN minus S, then in fact what's inside is the same as here. Okay, so this takes a little bit of cleverness, right, or pulling a rabbit out of a hat. But this is good. Why is it good? These are eventually small. These are eventually small. This S is kind of like that scalar multiplying, right? So there's lots of good things here. Okay. Now the trick here is to figure out which n works. That's what's harder here, okay? So let me suggest a way of doing this. We're going to do this one carefully, and I'm going to do it slightly differently than the book. I maybe simplify what's in the book, but I want to show you sort of how to deal with something a little more complicated, okay? And if you find this fun, then you're really an analyst at heart, okay? Okay, so here we go. Given so proof. Given epsilon bigger than 0. Well, okay, what am I going to do here? This is what's, I'm going to try to, of course, there's a triangle inequality here. I'll try to make this part small, and this part small. And what's not so obvious is how to deal with some of these things, right? Because if I have, so for instance, I could try to make Tn minus t smaller than epsilon over 3, right? But that's a little bit of a problem because there's an s in front, right? I don't know how big s is. So maybe I should try to make this epsilon over 3s, right? Are you with me? But wait, if I do that, then this becomes epsilon, or if I try to do this like epsilon over 3t, right? That's a little messy too, right? There's an s and a t. I'm kind of doing different things, and so maybe there's a way to simplify that. Let's let k, be the bigger of the two. Okay. We'll see why I'm doing this, but it's basically to avoid having to do different things for different terms. Okay. Now, it turns out, I'm just going to warn you that I'm going to leave a little space here because I might want to include more things in this k to make things work out nicely later. Okay. But this is sort of where you fiddle with it until you get everything to work. So here we go. What does this say? This means so that, given let k be this, then the point is there exists an n1 and an n2, just like over here. I'm picking two things for the different sequences, such that n bigger than n1 implies, help, Sn minus s is less than epsilon over, let's make it 3k because I'm trying to make this less than epsilon over 3. Okay? Do you see why if k is bigger than s and t, this thing will be small enough so that its product is less than epsilon over 3? Because that's as big as s, but k might be bigger. Okay, so this part times s will be less than epsilon over 3. That's a good thing. Okay. Similarly, n bigger than n2 will imply that Tn minus t is less than epsilon over 3k. Also, I'm looking ahead to what I need. With me? Okay. So what do you think I'm going to use as my maximum? Or what do you think I'm going to use as my n? I'm trying to find an n that works. Yeah, I hope that the maximum works, okay? But let's just try, right? This is where you're fiddling for a little while. So let's let big N be the maximum of n1 and n2. So if I'm far enough along in the sequences, then that term's small, that term's small. Oh, wait a minute, what about that term? That we haven't dealt with the first term. Well, then this implies, check this out, Tn minus St is less than or equal to, would you agree when I do the triangle inequality and split up those terms, what I get here from the first term is what? Epsilon what? Squared, maybe? Over 9k squared? Yeah? Plus, what does that term become? The s times Tn minus t? That's s over epsilon over 3k, yes? and epsilon over k is less than 1, so this becomes less than epsilon over 3, and the other one similarly.
Should that be less than or equal to?
I guess it could be strict now, if you want. That's correct. Okay. Now, we have a slight problem here. What do I need to be true here in order for this to be less than epsilon? I mean, the problem here is in the k, isn't it? Right? But I could do a few things to help me out. What could I do? There's also an epsilon squared, right? That's a little bit of an issue too. Well, there's many ways to fix this, okay? But let me just suggest one way. Isn't it true that if epsilon is less than 1, then epsilon squared is less than epsilon? Okay. Okay. That would be nice, wouldn't it? Okay, that's not exactly what I wanted, actually, just realized. Let's do something else. How about this? Would you agree if epsilon is less than k, I could get rid of one of the two squared terms? Because if epsilon is less than k, then epsilon over k is less than 1. And I could make that less than epsilon over 9k, right? So here we go. So I'm gonna do something, modify this to make epsilon less than k. And then, so this is because if I make epsilon over k less than 1, then this is strictly less than epsilon over 9k plus epsilon over 3 plus epsilon over 3. But now I can make this less than epsilon over 3 as long as I make k less than what? Less than 1. Okay. But now how can I make sure those happen? I can modify my choice of k, right? K just had to be bigger than s and t. And now, if I just make it bigger than 1, it makes that inequality true. Oh, yeah, sorry. That's right. If k is, this is what I want, actually. If k is bigger than 1, this becomes less than epsilon over 9. That's the right way. Thanks. A little worried there. Thank you. So I'll make this bigger than 1, and I'll make it bigger than epsilon. So here, I've just fixed this by making k bigger than st, 1, and epsilon. You can't stop me from going farther in the sequence if I need to. It's basically what I've done to make both these things true. Okay? So we've established what we wanted to establish as desired. Okay, I think I won't do all the other things, the other theorems like this that are in your book. Your book also talks about quotients or limits of reciprocals, and I encourage you to take a look at that. You have to be a little more careful there because with the limit of reciprocals, it's not necessarily defined if the denominator is 0. So you have to be just a little careful. All right. Any questions about what the strategy is for showing that sequences converge? Your goal is to find an n. The idea you start with is to bound the thing that you want to show converges, to bound the difference between the sequence and its limit. Okay? And you want to do so in terms of things you know are small. Okay, good. So that's a warm-up to sequences. Let's talk about subsequences. And I want to show you why it might be interesting to consider subsequences. So first, let's say what a subsequence is. So suppose you have a sequence Pn, and suppose you look at a bunch of indices, n1, n2, n3, ... and they're they're in order, arranged in order of index, n1 less than n2 less than n3, etc. So let this be in n an increasing sequence. Does it have to be infinite? Yes. Yeah, it's an increasing sequence that continues. Then a subsequence is just picking out imagine these are indices and looking at the corresponding points. Okay. Then P sub n sub I is a subsequence. So let's do an example here. Here's one. 1/2, 2/3, 3/4, 4/5, 5/6, ... This is a sequence. Would you agree? What's a subsequence? Well, a subsequence is basically picking out some sequence that's a subset of the previous sequence. Like maybe this might begin the subsequence, right? So here, n1 might be the second term, n2 is the fourth term, n3 is the fifth term. And would you agree this is P sub 2, P sub 4, P sub 5? It picks out a subsequence. Okay? It's just what you think a subsequence ought to be. Okay? Okay, so here's a question for you. Does this sequence converge? Yes? Willie, to what? To 1. Yes, okay. Does the subsequence converge? Yeah? To what? 1. Are there subsequences that don't converge? Does every subsequence of this sequence have to converge? Does it have to converge to 1? How many people say yes? How many people say no? What do you think it could converge to? What do you mean one element? Oh, subsequences, like sequences, are infinite. They're maps of n, right? So given that they are infinite, must there be a subsequence that converges? If the sequence converges, must every subsequence converge? Yes, in fact, that's true. So notice that this is, here's a question. If Pn converges to P, must every subsequence, which is just a sequence, isn't it, converge to P? And the answer is yes. And there's an easy way to see it, which is based on something we saw last time. If you recall last time, I think it might have been property F. We showed that every neighborhood of a convergent sequence contains all but finitely many points, right? So because every neighborhood of P contains all but finitely many points of Pn. So if that's true, then if the sequence converges to P, then it's easy to show the subsequence converges to the same P. In fact, you can tell how far in the sequence you need to go, right? If you need to go out to the 100th term to get the sequence to be within epsilon of the limit, then how far do you need to go for the subsequence to get to be within epsilon? Well, 100 would certainly work, wouldn't it? In fact, you might only have to go less far, right? Okay, so that's an important idea. Convergent sequences, well, their subsequences also converge and to the same limit. All right. What about sequences that don't converge? Could they have convergent subsequences? Sure. So here's an example. How about this? 1 pi, 1/2 pi, 1/3 pi, 1/4 pi, etc. I'm sure you see the pattern here. Does not converge, does it? But it has a subsequence that does. Can you see what? Good. That's certainly one. Pi, 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 pi. Yes, very good. There is a subsequence that converges. It's not the only subsequence that converges. What else do you see converges? Yeah, this also is another subsequence that converges. Okay. And there's also lots of other ones too, right? You could start off 1, 1/2, and then pi, 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 right? Okay. Okay, good. So, and what we do, we have a name for these limits. These are what we would call subsequential limits to a subsequential limit. Okay. Okay, so that begs another question. Not all sequences converges, but must every sequence contain a convergent subsequence? Oh, more interesting question. Must every sequence contain a convergent subsequence? How many people say, so just form an opinion, don't worry if it's right or wrong. How many people say yes? How many people say no? Okay, that's a lot of you. Give me an example of a no. Dylan. No, natural numbers. Okay. No. 1, 2, 3, 4. Does not have a convergent subsequence. Does everybody see why? If there were a sequence, that subsequence that converged to some number p, well, then you could show beyond some point you're bigger than 2p, and you'd never be close to p, right? Can't have a subsequential limit. Can't have a convergent subsequence. Jenny?
Is there a limit to how many subsequential limits you can have? Can you have like uncountably many subsequential?
Ooh, excellent question. What do you think?
Well, you can have at least countable because you could do 1, 1/2, 1/1/3, and just take all the numbers.
That's an excellent question. An excellent question. That's an excellent question. That's an excellent question. I think the answer is that it could be an uncountable set if you're talking about sequences of real numbers, but I'd have to come up with an example. So I actually encourage you to answer that question. I don't know the answer to that question. Don't you have to what? Index what? Yeah, but the elements of the subsequence, there are uncountably many subsequences. Right. You could. That's a great question. Somebody answer that question before the beginning of the next break. Yes, David.
If for every sequence that has both a lower and upper bound, would that always contain convergent subsequence?
Excellent question. In other words, is this the only way that you can fail to have a convergent subsequence? That the kind of question you're asking?
Yeah.
What do you mean by upper and lower bound?
Means that, no matter...
A bounded sequence, maybe?
Yeah, bounded sequence.
Must every bounded sequence have a convergent subsequence? Form an opinion and vote. How many people say yes? How many people say no? Okay, Bonnie?
No, I'm not saying no.
You're not saying no?
If it's bounded, doesn't the sequence converge? So then wouldn't it have
Must a bounded sequence converge?
okay.
Not necessarily. This is bounded sequence, not convergent. Okay. Must every bounded sequence have a convergent subsequence? How many people said yes? How many people said no? Okay. Interesting. Interesting. So if sequence is bounded, must it have a convergent subsequence? Most of you said yes. Which means we have a little work to do to help you build more intuition. Because in general, it's not true. Okay, and for general metric spaces, it's not true. So here's an example. Suppose my metric space were the rationals with the usual metric. Well, then here's a sequence with no convergent subsequence. 3, 3.1, 3.14, 3.141, etc. Dot, dot, dot. Which, as a sequence, doesn't converge in Q. And it also has no convergent subsequences that converge in Q. Now, of course, if it were in R, it would converge to pi. Okay, and every subsequence would as well. Okay? So it's not necessarily true that bounded sequences must contain a convergent subsequence. But what do you think is true? Harris? What do you mean by dense metric space? If the metric space is compact, do you think it's true? That is, if the metric space is compact, must every sequence contain a convergent subsequence? How many people say yes? How many people say no? Okay, many of you have not formed an opinion yet. Okay, well, we're going to answer that very, very soon. We're going to answer that very, very soon, yes. In fact, let's take a couple-minute break, and then after the break, we will try to answer that question. That's what you should be doing. Okay, so we had this question about when is it the case that sequences have convergent subsequences? And there was a conjecture that in a compact metric space, that must be true. So let me make a definition. This is a definition that's not in your book, okay? But I'm going to tell you this definition because it's a phrase that comes up a lot and it's convenient for our purposes. So we're going to call a metric space sequentially compact. Oh, maybe that was not a good time to introduce this definition, but we're going to introduce it here anyways. We'll call a metric space sequentially compact if every sequence has a convergent subsequence. And the question was, really, is it true that a compact set is also sequentially compact? Right? Does compactness imply sequential compactness? Because really, what does sequentially compact mean? It means this space is small enough that every sequence, even if the sequence doesn't converge, you can find something that, some subsequence that converges. So here's a theorem. Compactness basically implies sequential compactness. So if X is compact, then X is sequentially compact. There's the theorem. The way your book says it, in a compact metric space, every sequence has a convergent subsequence. Has a subsequence. And I'll be a little more explicit here. Not only am I saying the sequence converges, I'm saying converges to a point of that subsequence, right? So in a compact space X, every sequence has a subsequence converging to a point of X. And the only reason I'm trying to be explicit here is because there's sometimes this confusion. If you look at some space like Q, you look at this and you say, wait, this does look like it converges to something. It converges to pi, but pi is not in Q. What we're saying when we say we have sequential compactness is any sequence has a subsequence that converges to a point in that space, okay? Which this, clearly, Q is not sequentially compact. Okay?
So,
Yes, Aaron?
so we've got two terms, compact and sequentially compact, and compact implies sequentially compact.
Yes.
Terminology says that then sequentially compact does not imply compact. So what are examples of that?
Ooh, excellent question. So it turns out this is also a fact, which I'm not going to prove, that in fact they're equivalent. This actually jumps ahead a little bit, but this is a fact. And as a challenge, I'm gonna leave it to you to try to prove it. You have enough tools to do it, okay? But it's a little it's a little hard, okay? But I would love to see some of you prove it. Okay, but let's ourselves provide a proof of this theorem. Let me mention a corollary, actually, of this theorem. It's a very quick corollary before I prove this theorem, just to show you how useful this fact is. So an immediate corollary of this theorem is that every bounded sequence, so this gets to David's question, every bounded sequence in Rk contains a convergent subsequence. Do you see why? Rk is not compact. How can I say this is an immediate corollary? Bounded. You have a bounded sequence. Therefore, the bounded sequence lives in a compact subset of Rk. And therefore, it lives in a compact metric space. So it contains a convergent subsequence converging to a point of that set, which is in Rk. Happy with that? Okay. This corollary has a special name, which you sometimes hear referred to. It's called the Bolzano-Weierstrass theorem. Weierstrass theorem. Okay. Every bounded sequence in Rk contains a convergent subsequence. So let's try to prove this fact. Why is it the case that compactness is enough to give us sequential compactness? Compactness seems to give us lots of nice things, but what's true here? Well, here's one way to think about what's going on. You have some sequence in a metric space that's sort of hopping around some metric space. And this is some compact space X. Okay, well, there are a couple cases you could consider. You could consider the case where, for instance, if you look at the range of this sequence, that is all the values that are actually hit, if it's finite, then can you show that this sequence has a convergent subsequence? Yeah, Jacob's saying yes, because if you only hit finitely many things, and there are infinitely many points of the sequence, one of those points must be hit infinitely many times. Okay, so if R finite, then some value, some P in Pn is achieved infinitely many times. So you just use that subsequence. Okay? This is a version of the pigeonhole principle, right? If you drop infinitely many pigeons in finitely many holes, some hole must have infinitely many pigeons, right? Okay, so use this subsequence. Excuse me. Okay, what if R is infinite? If the range is infinite, then, got an infinite subset of a compact set. We have a theorem. Lindsay. Okay, and try to use that to kind of figure out where the... Okay. Okay, yeah, you could go back to the definition of compactness and proceed in a direction that you were going in, but we've actually done that already. We've done that already. Remember, if you have an infinite subset of a compact set, then that set must have a limit point, okay? And that's, oh, interesting. So that means there must be some point that is accumulated on limit point. There's probably many, but there's at least one limit point. Okay. So if R is infinite, then then by a previous theorem, in your book I think it's theorem 2.37, but we showed it in class too. If R is infinite, since X is compact, R has a limit point. Let's call it P. Now, the claim is that P must be a subsequential limit. Of what subsequence? Of what subsequence? Let's see. P1, P2, P3, P4. What subsequence is going to converge to P if you know this thing is a limit point? Take a neighborhood. Let's say 1 over n. Would you agree eventually one of these points lives inside? Let's say P101. Oh, but then you could take, how do you find another point how do I construct a subsequence that gets closer? How about 1 over n plus 1? And then take a point. Now, would you agree there has to be points inside, right? In fact, how many? Infinitely many. So, I mean, you could be unlucky if you pick a point here and it happens to be P50. You don't want your subsequence to go P101 and then P50, right? Because it has to increase its index. But since there are infinitely many, there must be one beyond P101 that's inside here, etc. So R has a limit, call it P. Use this to construct a subsequence. And I'm not going to write that out, but it's basically using this idea. Okay. ... Okay, so very nice, very beautiful idea. If the space is somehow small enough, compact enough, X must be sequentially compact. Every sequence must have a subsequential must have a convergent subsequence. Okay. All right. So we're gonna appeal to this fact often, and you'll see it come up quite a bit. The next thing I want to talk about. Oh yeah, question, Willie.
I was just going to say, alternatively, to construct a subsequence instead of taking infinitely many neighborhoods of different sizes, couldn't you just take one neighborhood and say, so take the p of the smallest index number, and then just every p higher than that that's
Yeah. So maybe a more formal way of saying that is we already showed a theorem that P, because it's a limit point of these things, would you agree that it must have a sequence converging, a sequence of these points converging to P? We've shown that already. But now the problem is when you write down that sequence, its indices may be completely mixed up. But then you could just, I think what you're suggesting is you could just fix that, right? So alternatively, there exists a sequence in R converging to P. We've already shown that. But maybe it looks something like this. Maybe P101, P50, P47, P210, P300, P1, P8, ... But would you agree, when you have found that sequence, it's not a subsequence technically because its indices don't increase. But there has to be a subsequence where the indices do increase. Why? There are infinitely many beyond this one, so there's got to be one that's bigger. That's the next bigger one. That's the next bigger one. And when you've picked these ones out, you have a subsequence. You could certainly do that as well. Okay, excellent question. Okay, so the other thing that I wanted to begin talking about is the very, very important notion of a Cauchy sequence. What is a Cauchy sequence? Named after the mathematician Cauchy. Now, the whole point of studying Cauchy sequences is to try to get a handle on the following question. How can I tell, can you tell if a sequence converges if I don't know its limit, if I don't know its limit already? In other words, a lot of our definition as it stands now requires us to know what the limit is in order for us to sort of figure out if it converges. Okay, everybody appreciate the question? It's like, you might have a sequence that you don't know if it converges or not, and you have no idea what its limit is. Is there a way to tell if the sequence converges without having to know its limit first? Okay, and so our idea is to define a kind of sequence that gives us a criterion for perhaps telling. So let's make a definition. Oh, so let me tell you what the idea is first before I make the definition. So you have a bunch of points, and I can't tell if these things are converging. But would you agree, if they converge to something that I don't know, they must be getting close to each other? That's the idea. If they do converge, then the Pn must be getting close to each other. That's the idea. So that's the motivation for our definition. There's a definition. We're going to say Pn, the sequence Pn, is Cauchy. It's a Cauchy sequence. And here's what it means. It's a Cauchy sequence if the following is true. For every epsilon bigger than 0, there exists an n such that, does it look familiar? Such that past some point in the sequence, the nth term, all the terms, instead of saying that they're close to P, will demand that they be close to each other. Okay? Such that, so how do I say that in formal language? If you have two indices bigger than n, that this implies what? Good. The distance from Pn to Pm to Pn, is less than epsilon. Now I want you to compare the two notions above. Okay. And now let's prove our first theorem. What's the relationship between these two notions? Are they the same? What do you think at least is true? Good. If it converges, it's Cauchy. So let's prove that. If Pn converges, then Pn is Cauchy. Proof. We can do this. All we have to do is try to show that points get close to each other. And you know they get close to P. So how are you going to show that they get close to each other? Okay, maybe like the other example, we should give our idea before we try writing down the proof. What do you think it is that I'm going to try to bound the distance between? So here's a proof idea first. What am I going to bound? What do I want to bound? Good. The distance from Pn, I better use this arbitrary metric space. Distance from Pn to Pm. What do I know is small? Pn to P and Pm to P. Well, can you relate those distances to this one? Triangle inequality strikes again. Happy with that? That's the idea. This is small eventually. This is small eventually. Therefore, this is small. And you can tell me at what point it is small. So here we go. Given, you can almost do this now, probably. Just tell me what to say. Given epsilon bigger than 0, probably state what you know first. There exists a n such that little n, bigger than big N, implies distance from P to Pn is less than, how about epsilon over 2? Okay. Oh, great. So what n am I going to use? Well, for both these terms, the same n works, right? So for this n and m bigger than big N implies the distance from Pn to Pm is less than, okay, now I'm just rewriting that idea, Pn to P plus P to Pm, which is less than, that's less than or equal to, this is less than epsilon over 2 plus epsilon over 2 equals epsilon as desired. Okay. That, in fact, shows that we found an n for any given epsilon, such that this holds. All right. Okay, great. So at least we know convergent sequences are Cauchy sequences. What about the reverse? Are Cauchy sequences convergent? How many people say yes? How many people say no? Form an opinion. Are Cauchy sequences convergent? How many people say yes? How many people say no? Okay, those of you who say no, raise your hand again. There are fewer of you now. You know I'm about to ask. Bonnie, can you think of an example? Interesting. Okay, that's all right. That's all right. It's okay. Look at this sequence in Q. Is it Cauchy? Yes, the terms get close to each other, but does not converge in Q. So look at this sequence. So the converse is not true. Smiley is Cauchy in Q, Well, so what am I saying? This is in Q. This sequence in Q is Cauchy, but not convergent. Ah, okay. So it actually behooves us to try to understand when the converse might be true. It's not true all the time, but if it's true some of the time, that's still pretty good, right? It would let us know, if we know that the converse is true in a particular metric space, then we'd have a criterion for testing whether a sequence converges by just checking if it's Cauchy. Okay? Okay, so let's create a definition that says what we want to be true. Okay, so here we go. We'll call a metric space X, we're going to call it complete if every Cauchy sequence converges to a point of X. So this is the kind of desirable property that we want. In a complete metric space, Cauchy means convergent. Okay? So you might wonder then, which spaces are in fact complete? What metric spaces are complete? What do you think? Q is not complete, yes? Q is not complete. Do you think R is complete, the real numbers? How many people say yes, R is complete? Okay. So Q is not complete. Is R complete? Really? So that's probably a good place to stop. And if you're really curious about the answer to this question, you can read ahead, which I assume you're already doing. But otherwise, we will try to answer this question next time. Okay? We'll see you on Monday. Oh, don't forget, there's homework due Thursday. And if you have questions,